Hello and welcome to the Geodic 2021 workshop for visualization. My name is Steffen Spichow. I'm a senior graphics designer here at MathroMarket, and in this workshop I will show you how to use the visualization features in Geodic 2021 to create impressive images and animations of your 3D image data, your microstructures and your simulation results. First, we clarify why visualization is so important that we even dedicated a whole workshop to this topic. Our brain processes visual information faster than text and numbers. We don't have to learn how to see pictures, but we do have to learn how to read. And even if the image does not communicate the core information, it can at least attract attention and make the interested person search the content for the desired information. A good visualization, no matter what kind, should make it easy for the viewer to acquire the desired information quickly and effortlessly. The viewer's expectation of the validity of the image in relation to the content plays an important role in this respect as well. The result of this workshop will not be a fixed setting that can simply be applied to all cases. Every microstructure and every result is different and has to be considered for itself. Rather, we will learn the basic principles and a solid understanding to be able to present our microstructures and results effectively in the future. To achieve this goal, the workshop is divided into 3 parts, each 30 minutes long, with a 10-minute break for questions after each part. In part 1, we will learn how we can visualize 3D image datasets and the associated segmented and voxelated microstructures. We will make sure that we find a good compromise between descriptive and attractive visualization. We will then save our results as image files. In part 2, we will use the knowledge from part 1 to visualize a result field from a simulation and the corresponding microstructure. In addition, we will get to know further visualization options for result fields. We will then save our result using the built-in GeoApp EasyImage. In part 3, we will look at the possibilities of video generation in Geodict. We will see how to create videos using the result viewer and how to apply and adjust the templates in the video dialog. Now, without further ado, let's dive right into part 1. First, we start Geodic 2021. You should have received and unpacked the workshop material files. The first thing we want to do is change in Geodic's project folder to the workshop files. In Geodic, we change the project folder by selecting the project folder icon in the toolbar and choosing Select Project Folder. Navigate to the location where we have saved the workshop files, select it, and click Select Folder. All Geodic generated files will now be stored here in our project folder. We will also find all materials that we need for this workshop here. Next, we load a so-called GRW file, our 3D image dataset. Load the dataset from the workshop materials in folder Part 1 by selecting File, Load Volume field from the menu bar. Navigate to the Part 1 subfolder of your project folder and then double-click the file called Artificial 3D Image Data.grw. A GRW is a Geodic RAW file and is Geodic's own file format for saving 3D image datasets in 8, 16 or 32-bit. In the Loading Volume dialog, you can view and select the content and information of the GRW file. We accept the default and click OK. What we see here now is the basic 2D visualization of the 3D image dataset with the default color scale on the right hand side. Up here we can slice through the dataset by dragging the slider with the left mouse. We can also use the mouse wheel to do this. To switch to the 3D mode, we use the icon in the toolbar up here. Although the 2D mode can be informative and interesting, the 3D mode gives us more visual possibilities to explore our data. First, we adjust the position and rotation of our camera in the visualization area to get a better look at our dataset. We rotate the camera by holding down the left mouse button in the visualization area and moving the mouse. We can change the position of the camera by holding down the middle mouse button or the mouse wheel and moving the mouse side to side or up and down. We can zoom by holding down the right mouse button and moving the mouse back and forth. I recommend a camera position that shows 3 sides of our dataset as evenly as possible. If you can already identify an interesting region like this, it should be visible. You can also adjust the position, zoom and rotation in the Camera tab of the visualization panel. To do this, select the Camera tab and you can influence the position in the transition X and Y fields and the zoom in the Z field. The rotation can be adjusted in the rotation heading, attitude and bank fields. In the center X, Y and Z fields, we can adjust the center of the rotation. This can also be done interactively by double-clicking on the volume field or the microstructure. This is especially useful when you want to take a closer look at an interesting region. To reset the camera settings, you can either use the Reset View button in the Camera tab up here, or right-click in the visualization area and select Reset View. We now set up our camera and then proceed to the next step, the visualization of our 3D image dataset. To adjust our 3D image dataset, we select the Volume Field tab in the visualization panel up here. Here we find the basic visualization settings for volume fields and 3D image datasets. First, we will have a look at the Color Map dialog that controls the color and transparency settings. To do this, we click on the Edit button at Color Map. The Color Map consists of 3 sections. The first section shows the raw data histogram, which shows us the distribution of the image data values. That allows us to set a minimum and maximum data range of the visualization. Here we can choose between different value ranges, manual, min-max, extended and percentiles. By default, it is set to percentiles with a minimum at the 1st percentile and a maximum at the 99th percentile. In the second section, we have the transparency setting, which maps data values to transparency values. Because this is disabled right now, this is grayed out and has no effect at the moment. Finally, we have the color section. Here we can define the colors for the data values. This setting is also reflected in the color scale that we can see here on the right side. First, we are going to change the colors in the color section. Our goal is to present our 3D image dataset here in the usual black and white look. We can either do this manually or we click on Load Color Preset and choose from a variety of predefined color variants. In this case, we select the black to white preset and click OK. You can see that Geodict has automatically applied our change and updated the view. Because this is going to slow us down in the next step, we disable this feature by unchecking the box next to Apply Immediately. This means that any change we are going to do is not reflected in the visualization area immediately, but once we click Apply, it will be updated. We now want to use the transparency to get a better view into our dataset. Although we can see the different material phases on the domain surface very well, we have no insight into the inside of the dataset. Our goal is to clearly bring out the white and light gray material phase. We will try to present those two in a particularly precise way, while still allowing us to take a look inside. For this purpose, we want to define a custom transparency transfer function. To do this, we first activate the transparency section by checking the box here. We can see the material phases represented in the data histogram in the background. We have the dark pore space, dark gray grains, lighter gray grains, and finally a cluster of white grains. We can also now manipulate this linear function by moving the control points and adding new control points to the function. We click on the free area between 2 points. On the right side, the button Add Point will be activated and we can add another point. We can also right-click in the free space between 2 points to add a point like this. The new point is automatically selected, which can be seen by the smaller white rectangle inside the black rectangle. On the right side, we can also see the position and the opacity value of the point. First, we add 2 more points here and here. The position of the first and last point is fixed. For these, we can only adjust the opacity value. We use an opacity value of 0.2 for the first point and 0.9 for the last point. We can either enter the values for the point directly into the opacity field here or manipulate the point with the mouse. To do this, we click on the point and hold down the left mouse button. Then we can change the value of the point by moving the mouse up and down. If we move the mouse left and right, we can also change the position at the same time. The direct input is recommended if you want to work precisely. We adjust the second and fifth point to the first and last point, 0.2 for the second point and 0.9 for the fifth point. And we will move the second point to position 11 and the fifth point to position 27. For the third and fourth point in the middle, we choose the value 0.9 and we will move them here to position 15 and to position 20. We take a look at the intermediate result with a click on Apply. We can identify our 2 types of cranes very well, but there is still some contrast missing. We add the same number of points in the color section by right-clicking in the free space in the color section down here and selecting Add Point. We also adjust their position to match them roughly to the points in the transparency section above, again by dragging them with the left mouse button. We press Apply again. For the final touch, we adjust the color values of the control points. The first and last point are already set correctly. We adjust the second point to the first one by setting it to black. To do this, we either select the respective point first and then click on the button Point Color, or we use the right-click dialog of the control point and select Change Color. In the color dialog, we select the respective color, black in this case, and press OK. The gradient between the 2 points is now a constant black. We do this also for the fifth point by choosing the color white, again using the right-click dialog here. For the 2 middle points, 3 and 4, we set the color to a medium gray. This corresponds to an RGB value of 3 times 127, either entered directly or by moving the brightness slider on the side while looking at the values in the RGB fields. We do this for both points. We press Apply, move the color map to the side and rate our result. If we navigate around our image data, we can see the distribution of the middle grains very well. And we can also evaluate the extent of the clustered grains here. Before we go on, we want to save the current state of our work. We move the color map dialog back into View and have a look at the 5 buttons in the lower left corner. In every Geodik dialog, the settings can be saved and reloaded. Additionally, you can load the built-in default settings, load the startup settings, and save the current settings as the startup settings. To save the settings in the color map, we click on the Save Current Settings to File icon in the lower left corner of the dialog. A file dialog opens and we can name our settings file, maybe My Color Map, and save it with a click on Save. I will quickly demonstrate the loading process by resetting the color map dialog to the built-in default and then reloading the saved settings here. Depending on the dataset, design specifications by the corporate design, or simply because of personal taste, a dark background may be desired. To do this, we first close the color map dialog and click on the icon for Color and Visibility Settings in the toolbar. In the Color and Visibility Settings dialog, we click on the button next to Background Color, which is white at the moment, and we click on the 3 dots. For a dark background, I recommend not to use black, but a very dark gray. This is more comfortable for the eyes. From experience, I recommend a value of 66 for the R, G and B color channels. Again, by direct input or by dragging. We press OK to accept the color. We also close the Color and Visibility Settings dialog by clicking Close. As we can see, this kind of visualization is also very pleasant and everything is still well visible. We now want to save the settings together with the color map settings. Before, we only saved the entries in a specific dialog, the color map dialog. Now we want to save all settings corresponding to the visualization. We can do this in the visualization settings here on the right side in Geodict. We open it by clicking on the double arrows. All settings for the visualization of microstructures, volume fields and so on are accessible through these settings here. We will have a closer look at the possibilities of the visualization settings later in the workshop. For now, we only look at the save and load function. The icons for saving, loading and resetting are the same as in other Geodict dialogs. We click on the icon for saving the settings here, give our file a name, for example my view status, and save it. That also allows us to experiment a bit with the colors, without losing our current progress, and reuse it for other similar datasets. In order to check that everything has worked, we first reset the visualization settings to the built-in default, with a click on the button here. Our visualization area is empty, but our data is still available. We now click on the icon to load our visualization settings here, select the file we just saved, and press open. After a short moment, we have reloaded the result we just saved, including background color and camera settings. With our settings saved, we can now experiment a bit. We open the color map dialog again and going to try out some other colors for our dataset. Again, we uncheck apply immediately first. In the color section of the color map, we look for points 5 and 6, the color points for the clustered grains in white, and change the color. Here you can now experiment a little or follow me in the choice of colors. For the grains in white, we choose a strong but light orange for both points, here and for this point also. For the medium gray grains, we choose a medium light blue for point 3, here this one. And for point 4, we choose a strong purple, here this purple, and OK. This creates a light, pleasant shade. To see our change, we click on Apply and wait a second for the update in the visualization area. Our dataset now has a pleasant complementary contrast and colors that harmonize with either light or dark backgrounds. We close the color map and save our visualization settings under a new name. Maybe call it My View Status Orange and Blue. And we click Save. Since we are about to switch to voxel visualization, we want to conclude the basic volume field visualization by finally saving our work as an image. For this, we position the camera in a comfortable angle and position. Maybe like this here. Then we either navigate via the menu, File, Save Image As, or use the icon Save Image As here in the toolbar. Here you have several options now. First and foremost is the resolution. If we keep this at current resolution, it will keep the visualization area resolution as is. If we choose custom resolution and keep aspect ratio, we can enter a custom width here, and the height will be calculated in order to maintain the current aspect in the visualization area. And we can also define a totally custom resolution here. There's also the option of selecting from a variety of presets, which are predefined standard resolutions or standard video resolutions. We will keep this at current resolution for now. Next is the option to crop all empty space. That means that we let Geodict automatically remove the empty background space in the image. Thereby, we do not have to go through an image processing software in order to cut the image. But of course, this also changes the resolution of the final image. The image is cropped to the next picture element, in this case to the material legend and the volume field legend and the axis cross here below. Without these legend elements, the domain borders of our dataset would be the next picture element. If we still want to have some space around the center of the image, despite the automatic cropping, we can choose Embed after cropping. For all sides around the image, we can define the free space individually. We can choose between absolute value in pixels or a relative value in %. For now, we don't want to embed space. Finally, we can choose whether we want to save the image with a transparent background or not. I would recommend to save images with a transparent background. This gives you the freedom to choose another background color later and to seamlessly integrate the image in a PowerPoint presentation, for example. For now, we uncheck it to save the image with our defined background in gray, and we also uncheck crop all empty space to get the image in the original size. If we are done, we press OK, give our image a name, maybe my first image, and press save. Now we can view our image by opening our Geodict project folder. We click on the project folder icon and select Open Project Folder. There we find our image and we can take a look at it by double clicking. As we can see, it was saved as expected. We don't have our image cropped and we also have an opaque background. We'll take a closer look at how we can clean up our visualization area later in the workshop. We close the image and go back to Geodict. Now that we have seen how to visualize gray value image fields, we are going to look at how to visualize segmented microstructures. The difference is that in the gray value fields, we have a continuous value domain, while in the segmented microstructure, we have a small set of discrete materials, with each voxel being assigned to one of the materials. Let's get started by getting rid of our data set by clicking on File, Discard Structure and Fields. Now we load our segmented microstructure. This corresponds to our example 3D image dataset and is already prepared as a Geodict file in the workshop materials. To load it, we either navigate via the menu, File, Open Structure, or click on the icon Open Structure in the toolbar. We navigate to the subfolder Part 1, select the segmented grain example.gdt and click Open. From the material legend, we see here that different material phases have been segmented and given their own material ID. The small grains were assigned to material ID 1, the middle grains to material ID 2, and the clustered grains to material ID 5. The pore space was assigned to material ID 0. The material ID colors we see here are the standard colors in Geodict. These were chosen to create the highest possible contrast between the materials. First, we will adjust the material colors. We will proceed according to the same principles as with our dataset in order to direct the viewer's attention to the area of interest. To change the color, we will open the color and visibility settings again. First, we set the background color back to white. Down here, click on the button and select white from the presets. Next, for material ID 1, the small grains, we click on the color button, currently red, and select white. This produces the least contrast against the white background, since we don't want to attract the viewer's attention to the small grains. For material ID 2, the medium grains, we click on the color button, currently green, and select the dark gray. This is a solid contrast against the white of the small grains. Next, we define the highlight color for the clustered grains with the material ID 5 that are currently purple. To comply with the corporate design guide, Here at Mass2Market, I will choose our corporate color, red. Last thing to note is that for each of the material IDs, we can actually make them visible or invisible. As we can see here, the pore space is invisible, which is the Geodik default, and the rest of the material IDs is visible. For example, we can make all material IDs invisible by unchecking these boxes here, and only show the pore space, for instance. But for this example now, we keep it as it was, with all material visible and the pore space invisible. We close the color and visibility dialog. Now we notice that the material phase of interest, the clustered grains here, to which we would like to direct the viewer's attention, is in the shadows right now. To change this, we will move the light source. We click on the icon for the light source in the toolbar here, and now the function of the mouse in the visualization area has changed to moving the light source instead of adjusting the camera. Also, a small icon in the visualization area has appeared. That shows us the position and direction of the light source. We move the light source by holding down the left mouse button and moving the mouse. We make sure that all sides are still clearly visible despite shadows, and that the shadow on this side here, the previously illuminated side, does not become too dark. So we adjust it like this, and as soon as we are satisfied with the result, we switch back to the mouse mode with the toolbar icon here. And now we again can adjust the camera with the mouse. Next, we will change the render style of our microstructure. We go to the Structure tab up here and have a look at the Structure mode. Currently, the selected render mode is Box Render. This renders the microstructure in the actual voxels. Next, we choose the Smooth Renderer, which creates a surface mesh from the voxels and displays it. This takes some seconds, and it depends on the amount of different material IDs that are in the structure, how much time and memory it takes. But therefore, we get a very nice surface visualization with gloss effects that support the perception of the surface topology. We also have a GPU-based renderer that displays the microstructure as voxels. It is much faster than the box renderer and the smooth renderer, which both work on the CPU. The limit here is the available graphics card memory into which the microstructure must fit with its resolution. Furthermore, not all visualization features are currently available in the GPU renderer. For our image, we are going to use the smooth renderer, so we switch back to it. Finally, we add some visualization effects that make it easier to see the topology and depth of our microstructure. For this, we switch to the Camera tab. There we activate Show Outlines, Show Halo, and Global Lighting. The global lighting takes some seconds to compute. The pore space around the grains is now more visible and easier to identify. Before we open the Save dialog, we first clean up our visualization area. For this image, we want to remove the material legend over here and the axis cross down here. We can do this either via the menu under View, Legends and Overlays, and remove the checkmark from Axis and Material Legend. Or we can use the visualization settings by clicking on the button up here on Detailed Settings. The visualization settings will automatically open in the right place, and we can clean up our visualization area there. Now that we have prepared our visualization area, we adjust our camera. And open the Save dialog up here again. This time, for a change, we select the Full HD preset right here and save it with automatic cropping. We also going to embed after cropping, and we're going to embed a 5% white border all around the image. And we keep the transparent background disabled to actually see how Geodik is cropping the image. Click OK, give your picture a good name, maybe my second image, and save it. Now we go to the project folder and open the image. As we can see, the image was properly saved with an embedded border all around, which roughly is the 5% we put in. We go back to Geodict and now we can save our visualization settings so that we can reuse them later, maybe as my view status with voxels. This completes the first part of our visualization workshop. We have visualized a 3D image dataset and the segmented microstructure. Thereby we got to know some visualization principles and some tricks in Geodict. We also saved our results as images. We leave Geodict open and return here after the questions and the break.